Last chapter, we left you with a problem. A test for a rare disease is 99% accurate. You take it. You test positive. What are the chances you actually have the disease? Most people say, 99%. Sounds obvious. The real answer? Closer to 9%. That's not a trick. That's not a typo. And by the end of this chapter, you'll not only understand why, you'll be able to spot this trap anywhere it shows up. First, before we run the numbers, we need two facts. Without both, the problem is unsolvable. Fact 1. The disease is rare. It affects 1 in 1,000 people. That's 0.1% of the population. Fact 2. The test is 99% accurate in both directions. If you have the disease, it catches it 99% of the time. If you don't, it correctly clears you 99% of the time. Those sound like good odds. Here's where the math gets uncomfortable. Forget percentages for a second. Think in people. Imagine 100,000 people all take this test. Of those 100,000, how many actually have the disease? 1 in 1,000, so 100 people. The test is 99% accurate, so it correctly identifies 99 of those 100 sick people. 1 slips through undetected. Fine. Now look at the other side. 99,900 people are perfectly healthy, but the test is wrong 1% of the time, even for healthy people. 1% of 99,900 is about 999 people. Nearly 1,000 healthy people who test positive anyway. So, total positive tests? 99 true positives, plus 999 false ones. That's 1,098 people holding a positive result. Only 99 of them are actually sick. 99 divided by 1,098. That's 9%. You test positive on a 99% accurate test, and there's a 9 in 10 chance you're completely fine. So why does this feel so wrong? Because when we hear 99% accurate, our brain locks onto that number and ignores everything else. We forget the most important piece of information we had before we even walked into the clinic. The disease is rare. That prior information, how common the condition is in the population, is called the base rate, and we have a deeply hardwired tendency to ignore it the moment any new, specific-sounding information shows up. The test result is vivid, concrete. It happened to you, right now. The base rate is abstract. It's about everyone else, in theory, somewhere. We weight the vivid over the abstract, almost every time. This is the base rate fallacy, and it isn't a niche statistical curiosity. It's one of the most consequential errors in human reasoning. Medical diagnosis is the obvious one, but it's everywhere. Airport security. A screening system flags a passenger as a potential threat. The system is highly accurate, but threats are extraordinarily rare. Most flagged passengers are completely innocent. The false positive problem overwhelms the true signal. If security teams forget this, resources collapse toward the wrong people. Spam filters. Your inbox is mostly legitimate. A filter that is 95% accurate will still occasionally flag real emails as spam, because the sheer volume of legitimate email means even a tiny error rate produces visible misclassifications. Criminal justice. Forensic evidence matches a suspect. The probability of a random person matching by chance is 1 in 10,000. Sounds damning. But if the test was run against a database of 1 million people, you'd expect 100 false matches, before accounting for actual guilt. Juries almost never hear that context. The math is the same every time. A rare event, an imperfect signal, and a brain that ignores the rarity. The correct approach has a name you'll hear more as this series goes on. Bayesian reasoning. The idea is simple, even if the algebra can get dense. You start with what you knew before any new evidence, the base rate, the prior probability. Then you update that belief based on how much the new evidence actually moves the needle. A positive result from a 99% accurate test on a 1 in 1,000 disease is real evidence. It does increase your probability, but it multiplies your prior, it doesn't replace it. You went from a 0.1% chance to a 9% chance. That's a 90-fold increase. The test did something, but it didn't get you anywhere near certainty because certainty requires a much higher starting point or a much more specific test. This is why doctors run a second test when the first comes back positive, not because the first test was broken, because they understand Bayesian reasoning, even if they don't call it that. Here's what changed for you in the last few minutes. When someone quotes you an accuracy rate, you now ask, accurate compared to what population? Among people who have the condition, or across everyone who gets tested? When you see a positive result, for anything, you now think, what was the base rate going in? And when a statistic sounds conclusive, you now feel the pull to ask, what's the denominator? That instinct is the beginning of statistical literacy. Not formulas, not jargon. Just the habit of asking what information is missing, and knowing that the missing information is usually the most important. Now you know that probability is a belief that updates with evidence. But that raises a question we haven't answered yet. Where does a probability come from in the first place? Not the one the test gives you, we've handled that. But the prior, the base rate, the number you walked in the door with. Sometimes it's obvious. A coin is 50-50 by symmetry. A die has 6 equal faces. But most real-world probabilities aren't handed to you from first principles. They have to be estimated, from data, from history, from observation. And the moment you start estimating probabilities from data, you've crossed into statistics. Next chapter, we build the bridge. How do you measure something you can't see directly? How many observations do you actually need before you can trust what you're seeing? It's more surprising than you'd expect. See you there.